So today we're going to learn how to solve a DE using an integrating factor. So we do start with a differential equation in standard form. So this is our DE in standard form. It can be y prime or dy dx, so it's first order. And we have a function in front of the y in terms of x, and that's our p of x. And our function in terms of x on the right, where p of x and q of x are functions of x, but they can also be just a constant. Let's look at some examples. So here we have 3 examples. You should pause here and try to find the p and q in each example. You probably want to make sure it's in the correct form before you say what p and q are. So example 1, it is in the right form. We have our function in terms of x on the right, just our single y right there. So p of x is equal to x squared, and q of x equal to e to the x. This is the one that we're going to need to solve it, though. We don't really need q of x unless you're using the formula, which I don't recommend. So this, we can see the function in front of y is minus 2. Don't forget that negative. And here we have to rearrange this. P of x is equal to minus 3. Again, I stopped writing out q of x because you really don't need to name q of x at all. So this is the first time that we're learning about an integrating factor. This won't be the last time. So what an integrating factor is we're going to call it mu of x. And it's basically this magical function that just works and helps us get the solution. So we call this the integrating factor mu of x. It's usually a function of x. It is the Greek mu. So what we do with any integrating factor that we're going to learn in this book, and by the way, if it's a special type of integrating factor, we will call it mu. So what you do is you multiply the standard form on both sides by mu of x, or just, if you want to just call it mu. And this is what it looks like. So I think what someone did is they looked at this and they said, hey, this looks like the product rule over here. You have a sum, you have y here, the derivative of y here. So that's what we're going to do. We're going to say that's the product rule and rewrite it. So we're going to rewrite this. So this looks like it's going to be the derivative of a product. Just to make it look a little cleaner, I do want to rewrite this without the of x's. I'll be going back and forth with adding the of x's and taking them off. So this looks like it could be the product rule, the derivative of a product. And so before I write that out, let's rewrite this without the of x's. So this is u y prime plus mu p y is equal to mu q. So this looks like it could be the derivative of the product uy. So we have some of it. Uy, the derivative of uy would be uy prime plus u prime y. So we'll come back to using that to be able to figure out what mu is. So that is equal to, on the right, mu q. Now that we've written this as a derivative and we want to be able to solve for y, because y is my solution of my DE, I can just integrate both sides, and it'll have to be in terms of x. So take of dx on both sides, integral of dx on both sides. On the left side, the integral and the derivative, they do cancel each other out. That was mu. So it's mu y, because those two cancel. is equal to, well, we don't know what mu of x is, we don't know what q of x is, so we don't know what that integral is. So we keep that that's equal to the mu times q dx. Now again, our goal is to solve for y, since y is our solution. So I divide both sides by mu. And here's our solution. We can see. So we can see if we utilize the fact that that is the product rule, it's really easy. The steps after that are easy to find y. You integrate, divide by mu, and you're done. So like I said, it works out really nice as long as we can find out what the integrating factor is. So in order to find the integrating factor, let's take a look at the product of mu y. Let's just go ahead and take the derivative. These are both functions of x, so again, we have to utilize the product rule. So that is mu y prime plus mu prime y. But what we have up there is we're saying that this product is equal to this left side. So this left side is mu y prime plus mu py. I'm just copying the left side. These are almost identical. These are identical. The y is identical. So it looks like we have to set equal y prime and up. So mu prime has to equal to mu p in order for this all to work. So all we have to do is solve for mu, and we have our integrating factor. So in order to solve for mu, the only method we've learned is separable. So we have to rewrite these as differential. Mu of prime is in terms of x, so this has to be the derivative of mu divided by the derivative in terms of x, which I just copy the right side. I separate. d mu equals mu p dx. Get that mu to the left. So now we can integrate both sides. We get natural log of mu equals, p is a function, it's not a constant. That's what we've got to remember here. So we don't actually know what the integral of p dx is, so we keep that, but we do want to solve for mu. So we do need to raise both sides to e. And then we'll get mu equals e to the integral of p dx. And that is our integrating factor. So here are the steps for the method of integrating factor. The first step is don't forget, we need it to be in standard form. So remember, it's everything's in terms of x. Q of x, p of x, y of x. Second step, we want to find integrating factor. And we work that out up there. So mu equals e to the integral of p of x dx. Once we found our integrating factor, we multiply both sides of our dE by our integrating factor. So remember, our formula is y prime plus py equals q. We multiply through by mu, mu, mu. Every term gets distributed. Fourth step, we need to recognize this is the product rule. So we rewrite as the derivative. It's backwards product rule. And my only advice here is you must check. Yeah, I was going to say please, but no, I say you must check. I'll tell you, the most common mistake is you forget if it's a minus. People forget the minus and you're off by a negative and it doesn't work out. Okay, so this is where you can catch that mistake if you check. Meaning, take the derivative of mu times y and see if it actually is equal to this. It should be. Next, integrate both sides and solve for y. Just divide by mu. Again, we're not going to memorize the formula. There is a formula for it, but you'll be way better off if we just learn early on the process. Understand the process, and then there's not much memorizing. Okay, so a couple common mistakes to go over before we do our first example. So the most common one is don't forget to start with the standard form. Again, if you check your product rule, you can catch this mistake also. So unfortunately, this one's a little harder to catch. Sometimes it's easy to catch if you can't integrate the right side because you needed that factor of mu, because some things are not integrable. And so other than that, just make sure you multiply both sides by the integrating factor. So you've seen me mention this, why it's a good thing to check, so I'm writing it. It's a mistake to forget to check the product rule because checking this will help catch other mistakes. Okay, so let's solve our first example. So is it in standard form? It's not, because we have something in front of the y prime. Standard form has just a 1 in front of it. So to get it into standard form, we're going to have to divide both sides by 1 plus cosine of x. So now it's standard form. Okay, so that means we can write out what p of x is. It's minus sine of x, 1 plus cosine of x. Mu, our integrating factor, is e to the integral of minus sine of x all over 1 plus cosine of x dx. So right now, I'm going to do a u sub, but I can use u because my u's look like that and that's my mu. But this is our first time with it, so I'm going to use a v sub instead, just so they don't look alike. V equals, I think I'll let it equal to the denominator. Mu is e to the natural log of v, which is v, but v is 1 plus cosine of x. So that's my mu. So now we multiply both sides. We take our standard form. We can see we're going to multiply both sides by 1 plus cosine of x, 1 plus cosine of x, 1 plus cosine of x, cancels there and there. This is the product rule. It's the derivative of mu y. Mu is 1 plus x, 1 plus cosine of x times y, which is equal to 2x. So we want to check, so let's take the derivative of that, d dx of 1 plus cosine of x times y. It's equal to, we copy 1 plus cosine of x times y prime, and then plus y times the derivative of this, which is going to be minus sine of x. And going back, this is the same as that. So we check it off. Yes. Okay. So now we integrate both sides. This is my check. So now integrate in terms of x, The derivative and the integral cancel. We get 1 plus cosine of x times y equals x squared plus c. Solve for y equals x squared plus c all over 1 plus cosine of x. And remember, this is just the general solution because it has our c in it. So we're going to solve this dE. We're going to use integrating factor. So it looks like because we have the 1, nothing in front of here, that it is standard form. So this is my p of x. So p of x is equal to just a constant 3. I told you it's okay to have a constant for that. So mu is e to the integral of 3 dx. Mu is equal to e to the 3x. By the way, I forgot to mention this above, but how come we're not writing plus c when we're integrating? So it turns out that you could, and if we did, it works, okay? Because we'll have the plus c. So if we did write the plus c, then we would have e to the 3x e to the c. But when we multiplied it through by here, this is a constant, and we'd be able to divide it through. Okay, so really, we don't need to write this because it does work for plus c. It works for a family of solutions. So we're just choosing c equaling to 0. Okay? So mu is e to the 3x. So let's multiply our integrating factor through the standard form. So we take our equation, multiply through by e to the 3x, e to the 3x, e to the 3x, our integrating factor. Rewrite this as the product, d dx of, it's mu, which is e to the 3x times y. Again, I always like to look at this, and it's not dy, it's not the dy, that's the product rule part of it, so it's just y times that. So you can always look at your first term to remember that. Equals e to the 3x times x. I'll put the x in the front, looks prettier. Now we integrate. We did that so that we can integrate both sides. On the left, the integral and the derivative cancel. On the right, it looks like we need to integrate that. We need to use our Calc 2 technique of integration by parts. Remember that? So u x v, we're finding dv will be e to the 3x. du is dx. This is dx there. Integrate that. It's 1/3 e to the 3x. And remember the formula? It is integral of u dv equals uv minus integral of v du. So this is just in case you forgot. Parts. Integration by parts. So it's going to be uv, which is 1/3 x e to the 3x minus integral of v, which is 1/3 e to the 3x times dx. Yeah, it's these two. V du, 1/3 e to the 3x dx. So we integrate this. Copy this. Just be careful though, that's not on the bottom. And solve for y. So dividing it into each, looks like it's going to cancel on the first one, cancel on the second one, oops. And we can bring it up as a negative exponent. I think that's the final answer, our general solution. So here's terminology. If we look at this, this is called a transient term, and this is why. Since if we look, we take x going to infinity. As x goes to infinity, the e to the minus 3x approaches 0, which means that term tapers off to 0 as x goes to infinity. That's what a transient term is. And it's important in a couple applied problems. So this method can actually be used on some nonlinear examples, but we're doing something different. So we can see this is nonlinear because we have the y on the bottom. So there's really not much we can do in how I presented. We can't get it into standard form. So what I'm going to do, if I had a single variable on the bottom, I could distribute. So I'm going to take the reciprocal of both sides. So this becomes x over y plus 1. So our equation is dx dy is equal to x over y plus 1. So basically we're doing this problem backwards. We're flip-flopping the x and y, okay? So when we're integrating, it's in terms of y. Before it was in terms of x, but we have dx dy instead of dy dx. So basically this is linear. It has to be linear to do it, but our original was non-linear. This is now linear in x. So let's write it in standard form. We'll subtract that x over y, and I'm going to write it so that you can recognize it's 1 over y times x, is my linear in x, is equal to 1. So here now I can see my p of x. Actually, it's not my p of x, is it? I just told you it changed. So my p, it's p of y. If you want to just write p, that's fine. It's 1 over y, negative. If you forget your negative, hopefully you'll catch your mistake when you check a product rule. Okay, so we found our integrating, well, no, we didn't find our integrating factor. We found our p, so now we can find our integrating factor. It's mu of y equals e to the integral of p of y, which is 1 minus 1 over y dy. So let's integrate this. E is minus natural log of y. We want to clean it up. E to the negative natural log of y, they don't cancel yet. So what we do need to do, this is where some people make some common mistakes. These cannot cancel because of this negative. We need to get rid of that negative. How do we do it? Well, if you just look at this, that's like a -1. We can use the power rule. So let's do that. Let's rewrite it because it's a logarithm. It's natural log of y to the -1. Power rule. Remember that rule? Now they cancel and we get y to the -1. Again, it falls apart if you do wrong algebra, so be very careful. So we have our integrating factor. So we multiply both sides by our integrating factor. I'm just going to use 1 over y. So this is 1 over y, 1 over y, 1 over y. We write this as a product. Again, if we just focus here, so we can write this as a derivative of a product, but remember, it's in terms of y now, so it's d dy, the derivative in terms of y, of this first part, which is my mu, and instead of the derivative of x in terms of y, it's just x. And over here, it's 1 over y. So before we go on, we do want to check this product rule. So the derivative in terms of y of 1 over y x is equal to, we copy the 1 over y, and then we take the derivative of x in terms of y, which is dx dy, plus we copy the x, I'll just put it there, and now we take the derivative of 1 over y in terms of y, that's y to the -1, which is minus y to the -2. And it does appear that this term is the same. We have the minus. This is y to the -2 times x. So they are indeed equal to each other. So now we can finish this problem by integrating both sides, but again, it's in terms of y. So we can see that this integral and the derivative will cancel, and we will get what's inside there, 1 over y x. And the integral of 1 over y dy is the natural log of y plus your c. And since our original problem was in terms of x, our solution is still y, but there's not a way to solve for this y, so we're just going to have to settle for this being our implicit solution. Okay, thanks.